thanks very much for asking me to talk today, NMI and Derek. He asked me to try and be a little bit controversial, so I hope you'll find something stimulating in the talk as we go through it. I hope I haven't mixed my metaphors too much in trying to make the UK a tiger economy, but you'll see where I'm coming from in the next few slides, hopefully. So what's the basic problem? Well, the basic problem is that Europe in general, and the UK in particular, have lost their way in manufacturing over the last 40 years. You can see from this table, this is from a McKinsey report. Germany's gone from 2nd to 4th. The UK has gone from 4th to 9th. France has gone from 5th to 8th. And Spain's gone from 9th to 14th. At the same time, all of the tiger economies have really risen in the ranks. And whereas in 1980, four of the top six manufacturing nations in the world were European, today only 2 of the top 6 are European and 4 are Asians. So you can see what the problem is. Allied to that is that private sector R&D spend has gone from top of the pile to being bottom of the pile over that same period of time. This is from the CBI. Now, you may think that's a coincidence. In actual fact, it's wholly expected because manufacturing contributes disproportionately to both research and development, private sector research and development, and to exports. So you can see from the chart here that manufacturing contributes 77% to private sector R&D spending and 70% to exports. And even more importantly, if you look at the right-hand chart here, you can see that the more complicated the manufacturing is, then the more closely located the research and development is. And obviously with the kind of industry we're in, it's very complex, and therefore research and development follows manufacturing. So the corollary here is that if you lose manufacturing, you lose R&D. So the outcome for the UK is wholly as expected, as you can see from the charts. Now, how have we got into this situation? Well, if you look at this chart here, this shows the distribution in R&D spending between basic research and an applied closer to market research and development in various countries. So we've taken the top 4 countries in manufacturing in the world, and you can see that they spend roughly 20% on basic research, but they spend about 80% on applied research and development closer to market activities to support their manufacturing. Europe in general has almost the opposite, 23% in applied research and 77% in basic research. And if you've ever been part of the framework programs over the last few years, you'll know that most of the money in the framework programs has gone on early stage research and development and very little into industry. And if you look at the public sector spending in the UK, there's an astonishing 90% of the funding put into basic research. So the research councils spend £4.5 billion a year. And the TSB, or Innovate UK as it's now called, has a budget of 450 million. And in the even closer to market activities, virtually nothing is spent. So for every £1,000 that are spent in early stage research and development, only £100 is spent in mid-tier sectors, and virtually nothing is spent in getting it into manufacture. So it's hardly surprising that we've fallen by the wayside in terms of global manufacturing. So the question is, how do we reawaken the lion to keep these tigers at bay? So I'm going to try and give you my insight into this. I think we should take a lead from Europe, because Europe has recognized what the problem is over the last few years, and they've put policies in place which readdress some of the core issues which Europe and the UK in particular faces. So they set up a high-level group in 2009 specifically to look at how they could get high technology back into Europe and reestablish the position. And for my sins, I'm the single UK representative on the second high-level group, which oversees the implementation of this. What the high-level group determined was that there were 6 key enabling technologies which underpin every advanced product in the world, whether it's a smartphone, whether it's a pacemaker, whether it's an electric car. And those technologies are nanotechnology, micro and nanoelectronics, biotechnology, photonics, advanced materials, and advanced manufacturing systems. And they also recommended that we should look in funding at something called the Technology Readiness Level Scale, which is shown on the bottom of this chart here. And it goes from TRL Level 1, which is the most basic research, blue sky idea, to TRL-9, which is absolutely full-out manufacturing. And this actually was developed by NASA for the space programs. And if you can imagine, number one was President Kennedy standing up on a stage in 1963 and saying, by the end of the decade, we'll send a man to the moon and get him back again. That was the blue sky vision. And 1970 was TRL level number 9, where he landed the man on the moon and got him back to Earth again. So there were two of the key recommendations. The third big recommendation was to approach the transition of getting knowledge and science from the very basic area through to the market, which has been a great failure of European and UK companies for many years, by having this three-pillar bridge over what's commonly called the Valley of Death. And the three pillars in the bridge are, first of all, establish research and technology organizations which will take the science and put it into a product, then develop industrial consortia and set up pilot line deployments so that you can actually get this into just before mass scale manufacturing, and then establish anchor companies in competitive manufacturing so we have globally competitive manufacturing facilities. This was adopted by the EU, and Neelie Kroes, who's the Chief Commissioner for the Digital Economy, has adopted all the recommendations of this report and set the goal of doubling the European chip production by 2020 from what it is today. So a pretty lofty ambition, but she is putting a lot of money behind this. And in particular, they're putting a lot of money behind pilot line deployment. Now, since I mentioned there's 6 key enabling technologies underpinning everything, clearly the one we're particularly interested in is microelectronics and nanoelectronics. So I thought I'd just say, devote the rest of the talk to this particular area, since that's what the audience is. Now, semiconductors have completely changed the world we live in. I guess we all know that because we live with this every day. But what's quite astonishing when you take a little step back is that here's Moore's Law, and Gordon Moore, the founder of Intel, he woke up in his bed one morning and thought, every 18 months, the number of transistors on a chip's going to double. Actually, he didn't just dream it up one day. He was predicting what's been happening for quite a number of years before that. But what's astonishing is that if you look at productivity measured on the left-hand axis in terms of calculations per second per $1,000, over the 40 or 50 years since Gordon Moore published Moore's Law, productivity has increased by 6 orders of magnitude. That's 1 million times. And that's been a major driver behind economic growth in every nation on the planet. So that's something that the microelectronics industry should be particularly proud of, because that's an astonishing achievement. And of course, we continue to see that happen. And just to put it in perspective, Sarah mentioned the aerospace industry. Here's another example of it. If in 1978, a flight between London and New York cost $1,900 and took 9 hours, if the airline industry had gone at the same pace as the microelectronics industry, that would now cost 1 penny and take 1 second. And we were driving cars which cost $25 that did 10,000 miles to the gallon. So that just puts in perspective what we've been able to achieve over that period of time. Now, it's all been achieved by miniaturization, as we know. So here we are in 1970, 2,250 transistors on an Intel 4004 chip. In 2014, 4 billion transistors on an IBM Power 8. Now, as we all know, that's kind of coming to an end, that whole process, because you can't miniaturize forever with the technologies we have. But if we look at it from a UK perspective, what's interesting is that we have absolutely world-class global leaders in design technologies. ARM, NXP, CSR, Wolfson, Imagination Technologies. All of these world-class companies, world-class design companies. And in fact, the world is recognizing this, because in the last 3 months, I think both CSR and Wolfson have been acquired by foreigners who really see the value in this. But the problem is, where are these chips made? Well, they're made in Taiwan, TSMC, UMC. They're made by Global Foundries in Singapore. They're made by Win Semiconductor in Taiwan, Samsung in Korea, PowerChip and SMIC in China. So if you think about the licensing model, we get a few percent of the revenue, the value of the product. But actually, all of the manufacturing and all of the 50% of the value goes to the economies who are manufacturing these things. So it's very difficult for us, to replicate these things. We can't go back. We tried very hard in the early 90s. If you recall, the UK government tried to bring a lot of chip manufacturing into the UK and failed pretty miserably because it was just trying to buy jobs, essentially, without growing things from scratch. But I think we now have a great opportunity to establish something in the UK, which is ours. And I think the next big opportunity is the next generation of semiconductors, which is compound semiconductors. And a couple of big advantages of compound semiconductors is they're at an early stage of deployment, but they use a process called epitaxy. And in epitaxy, you're no longer limited by horizontal physical constraints of lithography. You're only limited by atomic layer deposition. So in effect, you have no limitation to the thickness of films. And the second thing is that you can use a whole variety of different elements to design whatever property you want, whether it's an electronic property, an RF property, an optical property. So a huge amount of flexibility. And compound semiconductors have enabled the communications that we enjoy today. You wouldn't have the internet without compound semiconductors. It's the heart of all fiber optic systems. You wouldn't have a mobile phone system like we have today without compound semiconductors. So they've been instrumental in developing all of our complicated communication systems today. They're responsible for keeping satellites in space, for all satellite communications. But there are many, many, many more applications for compound semiconductors as we go through the future. So just as an example, IQE's wafers today produce something like 10 billion wireless chips, where in just about every smartphone there is, in the same way as Imagination Technologies and ARM and CSR and Wolfson are in just about every smartphone. So the UK has a huge amount to be proud of in terms of our contribution to global communications. And you can see it now going into many, many other forms of wireless communications. In terms of the broadband internet infrastructure, our wafers produce something like 2 billion photonics chips a year. And internet communications was actually developed in the UK by BT in the early 80s, in the late 80s. We have compound semiconductors for infrared sensors, for military, night vision, instrumentation, machine vision, security, and many other aspects. Compound semiconductors are much more efficient than silicon at converting sunlight into electricity. They're at the heart of every LED, which will replace every light bulb that you see around you today. In the next few years, everything will be gallium nitride-based LED lighting. And that will enable us to create indoors exactly the same kind of light that you experience outdoors, something called circadian lighting, where every light bulb is individually addressable, every light bulb is individually able to change color and to change intensity. So we'll have a huge amount of flexibility. Then we have power conversion. Gallium nitride on silicon is becoming a key material for efficient power conversion. And then compound semiconductors will eventually be in all of our CMOS chips as well. So a huge opportunity for this technology. We think it's a game-changing technology, far superior properties and more efficient than silicon, already a silent enabler to a lot of modern global society, and they underpin fundamentally all of the key enabling technologies. So we believe compound semis adoption is at an inflection point, and such a technology disruption happens once in just a few decades. Now the UK, fortunately, is actually quite strong in compound semiconductor technology. As you can see from the right-hand side, we have a lot of companies in the UK who either use or are involved in the manufacture of compound semiconductors, and our academic institutions also have spent an awful lot of money in developing compound semiconductor solutions. In fact, if you look at the three pillars that I mentioned before, on the left-hand side, you can see how much EPSRC has spent in the last 20 years on compound semiconductor technologies, £500 million. And yet we have no Caterpillar RTO, we have no real cluster in the UK, and we have no global scale commercialization other than just a few companies. So the question is, how do we put that right? Well, fortunately, the EU has come up with a scheme to help us do that. And in terms of micro and nanoelectronics, under Framework 7, there were 3 schemes. One was called ENIAC, one was called Artemis, and one was ETP EPOS. And these were schemes called joint undertakings. And in a joint undertaking, what it means is that if you've got a project, let's say a value of £10 million, then 50% of that 10 million comes from industry, 25% will come from the EU central funds, and 25% will come from the national governments. Okay, so for every £1 the national government puts into these schemes, they get a fourfold return because they get another £1 of their own investment coming back from Europe, and they get £2 more back from industry. ENIAC started to adopt this pilot line approach that the EU had recommended, the high-level group had recommended. And in 2013, the first 5 pilot lines were awarded. And you can see the project size. It ranged from 30 million for lab for MEMS to places to be the bottom one, 359 million euros for a project. So this is a pretty substantial investment in pilot line manufacturing. But you can see that most of the companies there are not UK companies. In fact, when you go to look at how much UK companies got out of this, here's the table of the first 5 pilot lines. If you look at the bottom, the total EU funding was 107 million euros. The country who got the most amount out of this was France. French industry managed to get 60 million support from Europe. The UK, on the other hand, only had 1 company involved, and that company only got 286,000 euros. We were outfunded by Malta, Finland, Sweden, Ireland, and Norway. And the reason for that was that the UK government didn't recognize that for every £1 it put in, it could get another £1 back from Europe. The French government, on the other hand, thought, aha, if we overfund this project, we will actually get taxpayers' money from the UK, from Germany, from Belgium, from the Netherlands, and everywhere else. So the French are very, very smart. And you can see that, in effect, the UK taxpayer effectively funded £20 million spent by French companies in microelectronics under ENIAC. Okay? A disaster for our industry. Now, under Horizon 2020, the new scheme is called ECSEL, Electronic Component and System European Leadership. It's the Horizon 2020 flagship program. Currently, it stands at a $5 billion program, but the demand from other countries has been so large that they're going to increase that, I believe, to $7 billion. And again, it's a joint undertaking, so it has the same mechanism, 25% from the member state country, 25% from the EU, and 50% from industry. And it's important to note that the member state contribution only supports that member state's countries in the project, the companies in the project. It doesn't support any other companies. So here we are, ECSEL, a joint undertaking between 5 billion and 7 billion. As I say, funded 50% by industry, 25% by EU central funds, and 25% by member states. Now, the EU central funds obviously come from the member states putting in their contributions. And the UK is one of only 9 member states who have a net contribution into the UK, into the EU. And we contribute about 19%, I think, to the total EU net budget. So in effect, if you look at the right-hand side column and break down the net contributions by country into the EU Commission central pot, the UK is effectively funding 360 million spend under ECSEL. The problem is that if we do not support that by matching funds from the UK, that 360 million will be spent by French companies and German companies and Dutch companies and Italian companies and everybody else. So all the other member states have really begun to understand how smart it is to overfund this. And so Germany's already committed 700 million euros to ECSEL, France 400, Belgium 350, the Netherlands 150, and Italy 100. Today, the UK has only committed £3.6 million. Now, with the help from the NMI, ESCO, Innovate UK, we have been lobbying the government really hard and aggressively to try and get the UK's commitment up to the kind of levels which means we will match our net contributions and actually get money back from Europe instead of continuing to put money into Europe. So we'll find out about that relatively soon, we hope. But if anybody has an opportunity to help push that agenda, then please, please, please help. And I'd encourage you all in your companies to think about aligning with programs within ECSEL. There's a very comprehensive website, but this is money that you can get from joining up with European countries to fund projects which are near market activities and get you really into manufacturing. Now, I'll tell you a little, just finishing off, I'll tell you a little bit about what we're trying to do in the UK on this particular scene. In Europe, as you probably know, there's today 4 semiconductor clusters in France, Belgium, Holland, and Germany. There's a couple of really powerful RTOs there. IMEC is one in Leuven, and CE Aletti in Grenoble. What we're trying to do is to create a compound semiconductor cluster and Europe's 5th semiconductor cluster in South Wales. And part of this is to create a compound semiconductor foundry. We have put a project into ECSEL to try and help us along. Has a number of product streams, including photonics, infrared, solar, LED, power, wireless, and CMOS. Already includes 17 UK participants, and you can see most of the largest companies in Europe. So these projects can be extremely powerful in getting you links into the rest of Europe. We've had an economic impact study done. The economic benefits are pretty high. Formation of between 25 and 50 new companies, creation of 2,500 to 5,000 new high-value jobs, and the creation of the world's first compound semiconductor cluster. And that's, although it will be located in the area around South Wales, it clearly includes all of the companies in the UK in compound semiconductors. Progress to date, Cardiff University have committed to a new innovation campus, £300 million, and a part of that is going to be a research institute in compound semiconductors. We are involved in creating a compound semiconductor research and technology organization. I've already talked about ECSEL and what we're trying to do with a project called Effortless. Obviously, it's everything but we're trying our best to get that done, and extensive lobbying with the help of ESCO and NMI. So, working together, getting behind ECSEL, really trying to exploit and get money from Europe instead of pushing money into Europe, working with the NMI and ESCO, really we need to work together and push the agenda forward and make Britain, once again, a great manufacturing nation. Thank you.